Hey, so in section 2.1, what we're going to be talking about is the secant line, which is going to tell us about the average rate of change, and the tangent line, which is going to tell us about the instantaneous rate of change. So here's the deal. Suppose that we create a graph, and it's marking how far away we are from home at a given time. Okay, and that time is how long we've been traveling. So here's the deal, is we leave our house and initially we are here. So when time equals 0, how far away are we from home? Well, we're going to be 10 miles away from home. Alright, so here's the deal. If this is our house, okay, boop, let's go ahead and give it a little door. Okay, what happens is that we start 10 miles away from home, and we're going to continue to travel, okay? And then when we hit the 2-hour mark, what now happens is that our distance between home and us starts to actually go down again. So we turn around and we come back until hour 3 when we're again 10 miles away. So let's go ahead and use this graph to answer a couple questions. So the first question, what is our average velocity between 0 and 1? So what's our average velocity between hour 0 and hour 1? So instead of using the word velocity, let's use the word speed. So between hour 0 and hour 1, what happens is that I go from being 10 miles away from home to being 40 miles away from home. What that tells me is that I went a distance of 30 miles. Now, when we're talking about speed, we don't just talk about distance, we talk about how long it takes us to go that distance. So if we're looking between hour 0 and hour 1, it took us 1 hour. So our average speed then would be 30 miles per hour, since the bottom is measured in hours. Now, how we did that is that we took 40 minus 10. So we took the difference in our y-coordinates, and then we divided it by 1 minus 0, which is the difference in our x-coordinates, to get our 30 miles per hour. Now for the next question, what was our average velocity between time 2 and 3? So again, if we look between time 2 and 3, let's go ahead and do this in a slightly different color. So at time 2, we were 70 miles away from home, and at time 3, we were 10 miles away from home. So that means that we went 60 miles in the span of an hour. However, notice that we're not talking about average speed, we're talking about average velocity. So velocity actually has another measurement other than just distance and time. It also has positive and negative. So if we're moving away from home, that means our distance is increasing, which means our velocity is going to be positive. If we're moving towards home, that means that our distance between us and our house is getting smaller, which means our velocity is going to be negative. So let's do the same thing we did on the last one. So we're going to take the y-coordinates and subtract them. So 10 minus 70 divided by, and we're going to take the x-coordinates and subtract them. So 3 and 2. Notice that when we take the x and y and we subtract them on the top and the bottom, they have to match. So 3 goes with 10 because that's the coordinate here, and 2 goes with 70 because that's the coordinate above. So what we're going to get is we're going to get negative 60, remember the top is measured in miles, per 1 hour. So our average velocity is going to be minus 60 miles per hour. Alright, so here's what we just found. First off, it's our average velocity. So if we're looking at our distance over time, we're driving away from home, and then we turn around and then start driving towards home again. Now, as you can see, we're not driving at a constant speed. We're kind of speeding up, slowing down about here, going home pretty fast, and then as you can see, we kind of level out right here and we slow down. So when we're finding the average velocity, what we're doing is that we're looking at the change in our y's over the change in the x's. Well, that feels really familiar to me. So let's look at this. I'm looking at the first one between hour 0 and hour 1. Now if I connect those two dots, what I get is I get something called the secant line. Now, a line actually has an equation, and that equation is y equals mx plus b, but when I find the change in y over the change in x, what I actually found is the slope of that line. So what that leads us to is our very first theorem, which is that the average rate of change of a function between points a and b is the slope of the secant line, which is going to be f of b minus f of a over b minus a, and that will equal m, our slope. All right, let's look at another example. So let's say that the distance a particle has traveled is given by the function f of x equals 1 over x. So what we want to do is we want to draw a graph of our function and the secant line between points 1 and 2. So if we look at this graph, between x is 1 and x is 2, we have these points 1, 1, and 2, 1 half. Okay, so the secant line is going to be the line that connects these 2 points on this graph. So this will be our secant line. Now the next question asks us to find the average rate of change from 1 to 2. Now, a couple of things I want to note is if we look at the picture, what we can see is that as we read it from left to right, we're going down, which means we're going to have a negative slope. Okay? Also, slope is rise over run, so if we look at this, we go 1 over and half down. So the slope is going to be, let's see, rise, we go down half a unit, so that's negative 1 half, divided by our run, which is 1. So our slope is going to be negative 1 half. Now let's actually find that using the formula. So looking here, my a equals 1 and my b equals 2, okay, because that's going to be the interval we're given. So the average rate of change is going to be f of b, which is 2, minus f of a, which is 1, divided by b minus a. So what we're going to get is 1 half minus 1 divided by 2 minus 1, which is going to give us a slope of negative 1 half. Great. Now the next thing we want to do is that we actually want to find the equation of the secant line. So remember, because we're looking for the equation of a line, it's going to be of the form y equals mx plus b. Well, we already know what m is. We know that m is going to be negative 1 half. So let's go ahead and plug this in. Now, to have the equation of a line, what you actually need is that you need to find b, which is the y-intercept. Now, the way that you find b is that we're going to choose a point on here. Whoops. We're going to choose a point on our graph, and we're going to plug that in for x and our y. Here's the cool thing. It doesn't actually matter which point you choose. So I'm going to choose this point here. Okay, I'm going to plug that in for my x and my y. So my y-coordinate there is going to be 1 half equals negative 1 half times 2, which is my x-coordinate, plus b. Now I've narrowed it down to a single variable and I can solve for b. So I'm going to get 1 half equals negative 1 plus b. If I add 1 to both sides, I'm going to get b equals 3 halves. So my equation for my secant line is going to be y equals negative 1 half x plus 3 halves. Awesome. All right, so the next example is the distance a car has traveled is given by the function g of x, The distance a car has traveled is given by the function g of x equals 3x squared plus 1. What we want to do is that we want to find the average rate of change on the interval between 2 to 3. So we're going to be finding the slope of the secant line there. So the formula is going to be g of 3 minus g of 2 divided by 3 minus 2. So remember, what g of 3 is means that you're going to plug 3 into this function. So 3 times 3 squared plus 1 is going to give us 29. Or no, I'm sorry. That's going to be 27 plus 1 is going to give us 28. Minus, if we plug 2 in, that's going to be 3 times 2 squared, which is 12, plus 1, which is going to give us 13. Divided by 1, which is going to give us 15. Now the next one is find the average rate of change on the interval between 2 and 2.5. Okay, so that's going to be g of 2.5 minus g of 2 divided by 2.5 minus 2. Now before we figure that out, I want to just point something out. On the whole rest of these, that 2 stays the same, but we're changing the b value. So that means that this value here is going to be changing. So for example, in the next one, that's going to be g of 2.25 minus g of 2 divided by 2.25 minus 2. Okay, and the rest of them, all right, so what I'm going to end up doing for this problem is I'm going to end up doing a lot of calculations. So I want to show you guys how to kind of fast track this using an online tool called Desmos. So go ahead and get on your computer and open up desmos.com, and I'll do that right now as well. Alright, so once you open up Desmos, the first thing that we're going to do is we're going to enter in our function value. So our function is g of x equals 3x squared plus 1. So let's go ahead and plug that in. So I'm going to type it just as it shows up on the paper, 3x to the second plus 1. Remember, it's important to name it g of x. It's going to come up in just a second. Now, after you enter in your function, you're going to go to plus, table, and we're going to change this x sub 1 to just x. And we're going to change this y value. Now, when we change this, we're going to make it g of x minus g of 2 divided by x minus 2. Now, the reason we entered it like that is because if we go back to the problem, notice that it's our b value that's changing all the time. Okay? The 2 stays constant, so we're going to let that b value be this variable x. Now what I can do is I can enter those different values, so 2.5, 2.25, 2.125, and 2.001. So when I go back, I can just enter in those values instead of going back and forth and doing all that work over and over and over. Well, here's something that I want to ask is, what do we notice is happening as the interval becomes smaller? So as the distance between a and b gets smaller, so here it's a whole distance of 1 away. Then we go down to a distance of a half, then a quarter, then an eighth, okay, all the way down to a thousandth. What's happening is it looks like our number is actually approaching a certain value. And what it looks like is m is getting closer to 12. So let me show you what we just did graphically. So what I have here is I have a picture of our function, 3x squared plus 1, and that is in the red, and then in the blue I have our secant line. So here we have the point 2, and here we have the point 3, okay, so 3, 28, 2, 13. And what we did is that we started pulling those values closer and closer and closer. Now what happens is as we get them closer and closer and closer, we no longer have a secant line. What we're going to have is a line that goes through only one point of our graph, and that line is going to be called the tangent line. Now what the tangent line is is that it is going to give us the instantaneous rate of change. So the slope of the tangent line is the instantaneous rate of change, and its formula is going to be very, very similar to the secant line, except for we're going to choose b values that are very close to our a values. So let's look at an example of this. By the way, instantaneous rate of change is like instead of driving for an hour and then using your distance over the time that you traveled, instantaneous rate of change is like looking at the speedometer. It's knowing exactly how fast you're going in the moment. So let's say that we have a function h of x equals, and by the way, I'm going to just go ahead and change this. We're going to call it f. We're going to go ahead and call this one f too. So let's say we have a function f of x equals x cubed minus 2. So the first thing we want to do is draw a function of f of x and draw the line tangent to the point a equals 1. So when x is 1, my y value is also going to be 1. Okay, so what I see here, oh no, I'm sorry, my y value is negative 1. You can't really see it very well. Negative 1. So the tangent line is the line that goes through that point, and it's going to hug my function very, very closely. Okay? So the reason I like to draw a picture whenever I'm doing these problems is because the picture kind of gives me an idea of what my slope should be. So just from looking at this, I know that my slope should be a positive slope. Now, to estimate the instantaneous rate of change, what we're going to do is that we're going to choose values really close to 1. Okay? So for example, I chose the point 0.9, 0.99, 0.999. You could also do other values close to 1, so you could do 1.001, things like that. So we're going to go back to Desmos, and we're going to do it the quick and dirty way like I just showed you guys. So let's go ahead and go back here. Okay, so we have f of x equals x to the third minus 2. Okay, but now this time we are going to have f of 1 minus f of x divided by 1 minus x, because the 1 stays the same, the x value over here is going to change. So we're going to look at 0.9, 0.99, 0.999. So what I see is that my slope is going to be 2.71. So what I can see is that my slope, as that interval gets smaller, is going to go from 2.71 to 2.9701 to 2.997. Okay? Now, if I approach it from the other side, so instead of getting closer over here, what if I try to get closer with values a little bit bigger than 1? So let's just go ahead and do 1.001. Okay, so 1.001. I'm going to get 3.003. So it looks like as our interval gets smaller, so as b gets closer to a, our slope is approaching. So what's happening is that as this value gets closer to 1, it looks like our slope is getting closer to what value? It looks like our slope is getting closer to 3. So we would say as x gets closer to 1, m looks like it's getting closer to 3. Which lines up with what we had in our picture. We knew that we were going to have a positive slope. Now the next thing we want to do is we want to find an equation for the tangent line. So first off, our tangent line is going to go through the point 1, comma, negative 1, and I know that from the picture. Okay. I also know a equals 1, that's my x value, and if I plug this in, I'm going to have 1 minus 2, which is going to give me negative 1. And I also have that my slope equals 3. So like the previous example, I'm going to have y equals 3x plus b. I'm going to plug in my x and my y. So when I solve for b, what I'm going to get is that b is going to be negative 4. So my equation will be y equals 3x minus 4. Now let's just go ahead and go back to Desmos and just check our work. So if I go back here, what I'm going to do is I'm going to type in y equals 3x minus 4. And what I get, if I zoom in on this for you guys, is I get a line that goes through the point I wanted it to, and it is perfectly tangent to my original function. That means it touches it but doesn't necessarily go through it at multiple points. Awesome. All right, let's look at one more example. So go ahead and pause the video and try to work through this one on your own. Then when you're done, come back and double check your work. All right. So the point 5, 1 lies on the curve y equals 3 over 8 minus x. So if we plug in 5 for our x value, we're going to get 3 divided by 8 minus 5, which will give us 1. So that's where that 1 comes from. What we want to do is that we want to estimate the instantaneous rate of change at the point 5, 1. So if we draw the tangent lines, remember, that's the line that hugs our curve and just passes through that one point. So again, it looks like our slope is going to be positive. It also looks like it's going to be a little bit on the low side, so probably less than 1, but we will see. So again, when we're estimating the instantaneous rate of change, we're going to use that secant slope formula, but we want to choose values very close to 5. So again, I'm going to go to Desmos and kind of be a little cheater. So we have 3 divided by 8 minus x. Okay, and again, I'm going to go ahead and pull up my table. So I'm going to make this x. I'm going to make this f of 5 minus f of x. All divided by 5 minus x. So let's see, let's do 4.9, 4.99, 4.999. Okay. So what I have is I have 3.225 or 0.3225, 0.3322, 0.333. Now another thing we can do again is instead of picking values that are smaller than 5, so like 4.9, 4.99 approaching from this side, you can also choose values that are a little bit bigger, so like 5.1, 5.001. So let's plug those in and see what we get. All right, so we get 3.44 or 0.344 and then 0.33. So here's what I'm noticing is that as I'm getting closer to 5, what it looks like is these values are getting closer to 0.33 repeating, which means that m is probably getting really close to 1/3. Now again, I want to find the equation of the tangent line. So I have the point 5, 1, and I have the slope 1/3. So remember, y equals 1/3 x plus b. We're going to plug in our x and our y, so we're going to have 1 equals 1/3 times 5 plus b. Okay, so we're going to have y equals 5/3 plus b. Got to subtract 5/3 from both sides. Okay, so we're going to get negative 2/3 equals b. So the equation for this tangent line minus 2/3. And again, we can double check our work by going to Desmos. And typing that in. So we're going to have 1/3 x minus 2/3. Okay, and remember we have to go through the point 5, 1. And it looks like we do, so we did awesome.